In this problem, we're dealing with diffraction and interference all in the same problem. I have 532 nanometer green laser light incident on a pair of slits. The width is given by 0.1 millimeters. The separation distance is 0.3 millimeters. And it's the actual slit width that causes the diffraction pattern, and then it's the slit separation that causes the interference pattern. And what we're looking for in part A is the smallest angle for which a diffraction minimum suppresses an interference maximum. And I'll post a link to where this formula was first derived, but we have a formula for where the diffraction minima occur. Those happen where asin theta is equal to n lambda, where A is the slit width, and n is 1, 2, 3, and so on. We also have a formula for where the interference maxima occur. And I'll post a link to where that formula was derived as well. The formula is dsin theta equals n lambda, where d is the slit separation, n is 0, 1, 2, 3, and so on. So how do we find this angle where a diffraction minimum is suppressing an interference maximum? I'm going to go ahead and plug some numbers into the diffraction minima formula. And I'm just solving for sine theta here. We put in the wavelength of 532 times 10 to the negative 9 meters. That's 532 nanometers. And then our slit width was 0.1 millimeters or 0.0001 meters. If I do the same thing for my interference maxima, I have sine theta equals n lambda over d. And so I get n times 532 times 10 to the negative 9 over 0.0003. Now the question is just, can I pick the n's for these two different formulas so that I make the angle pop out the same? And I quickly see that if I make the n for the diffraction 1, and I make the n for the interference 3, I'm going to end up with the same angle here because that 3 will cancel the 3 in the denominator in that second formula. So we actually got this to happen at the first diffraction minimum. So I know that I'm looking at the smallest angle where this is possible. And that angle must be the inverse sine, 532 times 10 to the negative 9 over 0.0001. When we run the numbers on this, we get about 0.305 degrees. This is the location where the n equals 3 interference maximum is being crushed by the n equals 1 diffraction minimum. In part B, we're following up to projecting this pattern on a screen and then trying to figure out how far this feature is that we just computed, how far it is from the center line. So we're projecting onto a screen that's quite distant. It's at a distance of 10 meters. We just figured out that this point where the first diffraction min suppresses the third interference max, that happens at about 0.305 degrees. And to figure out how far that is from the center line on the screen, we just have to use a little bit of trigonometry. I see that the tangent of theta is y over 10. And this means y is 10 tangent theta. And when we run the numbers on this, we get 0.0532 meters, which might be nicer to write as centimeters. So that's 5.32 centimeters. And that's it. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.